All right, in this video, we're going to be working some area and perimeter examples for AP Calculus. So let's look and see what we got first. So unless otherwise indicated, arc length integrals will require a calculator. That's true in general. These are pretty hopeless in general to anti-differentiate the square root of 1 plus f prime of x squared for a given function f. Okay, so we're going to look at finding the area of region 1, which I think I'm going to just get some more paper. This is not going to be enough room for me to work. So let's draw our own version of R1. So R1, it's here, and it's touching the graph of y equals square root x. And that's probably, let's call this R1 right here, right? And so this is y equals 1, and this is y equals the square root of x. And so if we want to find the area, we're going to integrate top minus bottom as we move along x being from 0 to 1. Okay. Representative piece is going to be 1, y equals 1 minus y equals the square root of x, top minus bottom. So the area will be the integral from 0 to 1 of top minus bottom. So it'll be 1 minus square root x. And I'm going to integrate that with respect to x. Okay, and we can do this. We're going to find an antiderivative. Plug in the top and bottom, so that'd be 1 minus 2/3 is 1/3 minus, okay, 0 minus 0 is going to be 0. And so that's going to be an area of 1/3. Okay, it's R1. Okay, number 2, find the area of region R2. We can do that. All right, so R2 is the one that's between the two curves, and you can see it over here, squared x, x squared. So I will go and I will make myself a little sketch of the region. I will say, all right, I'm not going to actually label the curves because I think you know what they are. And if you don't, you'll come to be very familiar with this drawing over the next few homeworks. I think I just keep using it. All right, so area of region R2 is going to be, okay, top minus bottom is going to be y equals square root x minus y equals x squared. So when I integrate, it'll be the integral from 0 to 1, because that's x equals 0 and that's x equals 1. And I'm going to be top minus bottom is square root of x. I might even just go ahead and write it as x to the 1/2 just immediately. Minus bottom. And I'm going to be integrating as x runs from 0 to 1. Okay. And so I'm going to find an antiderivative. Plug in 0, plug in 1, and subtract. I guess plug in 1, plug in 0, and subtract. So I'm going to say 2/3 minus 1/3. When I plug in 1, it's going to be 1/3. Minus, both of these areas are 1/3. Wouldn't have thought that, but they do kind of look, they look the same. I think if you thought about finding these with an integral in y, you would see why they were actually the exact same. I'm starting to understand myself. But somehow when we go to turn these into volumes, that does not always hold. So anyway, the perimeter of R3, okay, it doesn't say otherwise, so it is going to require it's going to require an integral. I mean, a calculator to run the integral. So if I draw you a picture of R3, it would be that. Okay, so I have 1 here, 1 there, and y equals the square, nope, that's not y equals square root x, that's y equals x squared, pardon me. So call that y equals x squared. Well, I know that I can get perimeter. I can start by adding 1 plus 1. I'm going to have to integrate, okay, as x runs from 0 to 1, the square root of 1 plus dy dx squared. If y equals x squared, dy dx equals 2x. All right, I'm going to need a calculator. Right here. So let's see if I can scoot that up a little bit. 2 plus the integral from 0 to 1 of the square root of 1 plus, okay, you could put 2x and then put parentheses around it and square it, or you could just know that 2x times 2x is 2 times 2 multiplied by x times x, and then I'll just integrate that. I get 3.479. Okay, got to remember 3 decimals every time. That's the perimeter. Okay, and the perimeter of R2, yeah, let's flip that over real quick. And I'll give you a sketch of R2. Okay, that's y equals square root x, and this is y equals x squared. The perimeter, I'm going to have to just add together the arc lengths of those two curves. Okay, so the length of the square root x one, say, will be the integral from 0 to 1 of the square root of 1 plus dy dx is 1/2 x to the negative 1/2. X plus the integral from 0 to 1 of the square root of 1 plus, well, this one's going to be the same as what I'd already computed. Okay. And so what I'm going to do is I'm going to go over here. I'm going to ask for the same thing again. I can really not see that. So I'm going to ask for that, go over here, delete the 2. Probably could have just done that, subtracted 2, but it's all right. Plus another integral from 0 to 1 of a square root of 1 plus, okay, dy dx squared is going to be, okay, if I square the half, I'm going to get a fourth, and then I get x to the negative 1. So, whoops, 1/4 x to the negative 1. So maybe, I don't know, just use a fraction bar. 1/4x dx, and I'm going to add that up. Thinking. Oh, pardon me. I should have not asked you that one. I'm remembering now that it's not going to like this integral because of basically, okay, I kind of, I don't know, have my doubts about this integral a little bit, because if you look at the integrand on the second integral, if you think about what happens at x equals 0, you're integrating the square root of 1 plus 1 divided by 0, and that's, I don't know, 2 almost 3. It seems kind of reasonable, like it could be the length, but I don't know. This is an improper integral, and we haven't studied those yet. So, and I think, I don't know, I can't say for sure if that one's going to exist or not. Okay. But next best thing is just copy down what the calculator told me, 958. And don't worry, I won't be giving you, something like that where it's actually an improper integral. I'll be more careful in the future. Okay, find the length of the curve shown in the figure. Okay, 2/3 x to the 3/2. That means that dy dx is equal to 3/2 of 2/3 is 1, x to the, subtract 1 from the power, that'll be x to the 1/2. Okay, so the length is going to be the integral from 1 to, it looks like 8, of the square root of 1 plus dy dx squared is going to just be x dx, okay. And now this is going to be something I can find an antiderivative for, because this is 1 plus x to the 1/2 power. I'm going to, try just adding 1 to the power and dividing by the new power. And at chain rule level, it's going to work out just fine. So this is an antiderivative. And we'll let x run from, 1 to 8. Okay, not really sure what we were supposed to do here with this 1 plus x here. Like we can't take 2 to the 3/2 power. We can. We've got to call it 2 to the 3/2 power. But it's all right. And so this will be 2/3 of 9 to the 3/2 is going to be the 27, because you take the 1/2 power of 9, that's the square root of 9 is 3. 3 to the 3rd is 27. So I'm taking 2/3 of 27 minus 2/3 of 2 to the 3/2. And one thing we saw at the end of the previous semester was that 2 to the 3/2 can be written as 2 square root 2. And maybe I'll just write like that. That's an exact value of the arc length. That'll be good enough for us. Write an expression involving just one integral that gives the area of the shaded region. All right. So what we need to do, we need to get ourselves a representative rectangle. Okay, this is the graph of f. It doesn't look like it because they kind of switched on us, but okay, f is on top, g is on bottom. And so I'm going to just say, well, I'm going to integrate from x equals -2 to x equals +2. So this will be a -2, that'll be a 2, and this will be dx. And the integrand is going to be top minus bottom, right minus left. This is top minus bottom because it's vertically simple or whatever. And so I'm going to say it's f minus g. And if you felt like you needed it, you could put some sort of grouping symbol around those to indicate that's the integrand. But if you didn't want to, that'd be cool too. All right, for the next one. Let's see, I haven't used this blue pen in a while. Okay, it still works. Okay, this one, f of y and g of y, gets kind of your first hint. Second hint, like if I went vertically, I'd be going on the same curve twice, and then on this same curve. That sounds difficult. So what I'm going to do instead is I'm just going to integrate in y. And so on the right, I've got g of y, and on the left, I've got f of y. And this, I'm going to be integrating along the y-axis, so I'm going to need to let y run from -3 to +1. So this is going to be, whoops, you can't really see that. Let's see how I could scroll that down a little bit. All right, so y going from -3 to +1. So it'll need to be dy. And then on the inside, I've got right minus left, greater minus lesser. So g of y minus f of y. And then if you want to, you could do a little bit of that. But if you didn't want to, that'd be fine too. Next one is one of these that could go either way in terms of integrate with respect to x or integrate with respect to y. Okay, I think what I'm going to do is I'm going to kind of do my own thing over here. I'm going to write both expressions. I'm just going to kind of, I'm going to redraw the graph. Oops, did not realize that was not the x-axis, so we'll go about like that. All right, if I wanted to go in terms of x, well, I'm going to have pretty much my top minus bottom is going to be these two horizontal lines, y equals 6 minus y equals 2, until here, or really here is where it switches. And then my top minus bottom is going to be 6 over x minus 2. Okay. So I'm going to need, if I've got two different things going on, I'm going to need two different integrals. Okay, that's why it said an expression involving an integral in x. So what I'm going to do is I'm going to start off by saying, well, I'm going to integrate from 0 until they intersect, which is looking like it's happening at x equals 1. So I'm going to go from 0 to 1. Top minus bottom is 6 minus 2. dx plus the integral from 1 to, that's looking like 3, of top minus bottom is y equals 6 over x. Minus y equals 2. Okay, and that's my expression in x that gives the area of the region. Okay. Now I'm going to do that process again with respect to y. And I think you'll see that it might be a little easier to compute with respect to y. But not too much easier because, of course, we can just say, oh, wait a second, that's a 4x1 rectangle. And then we can run this integral, which is actually, you'll see it'll be the exact same as running in y. But before we go there, we just need to, there's 2, here's 6, there's the curve. That will work. If we wanted to run this in terms of y, well, then we would be going from here to there. And we could go up and down, and on the right we would always have that curve, and on the left we would always have the y-axis. It seems like a little bit better. We'll definitely only need one integral for this. Okay, so on the right we have y equals 6 over x. But if I'm going to integrate in terms of y, I need to solve for x in terms of y. So I'm going to multiply both sides by x, and I get xy equals 6, and then I'm going to solve for x by dividing both sides by y, and I get x equals 6 divided by y. And then over here, the y-axis, this is the set of all points where x is equal to 0. Okay. Now the y-coordinates, because I know I'm going to need to integrate in terms of y, really specifically because the question asked me to. I'm going to say that y starts here at 2 and goes up to 6. So I'm going to go over here. And yeah, you can see that still. I'm going to integrate from 2 to 6 in y. And the integrand is going to be right minus left. Okay, well, right is x equals 6 over y. Minus left is x equals 0. Okay, so that's something that we could integrate. But it didn't say find the area, it just said write an expression, so I just wrote the expression. If you needed to practice your integration, that's where you would take this. The next couple of steps, you'd find an antiderivative for 6 over y. With respect to y, you would plug in 6 and 2, you would subtract, you would get yourself an area. Okay. Find the value of b so that the line y equals b splits the area enclosed by a few different things into 2 equal parts. All right, so let's get over here. I'll try a different pen. That one wasn't working so well. So y-axis y equals 3 and the curve y equals x squared. Okay. It's much better. Okay. Y-axis y equals 3 and y equals the square root of x. Okay, I see what they're talking about. They're talking about this kind of triangle-looking thing. And, okay, the line y equals b. That is a horizontal line. So I'll kind of eyeball it a little bit. Say, well, I think it's probably going to be about here. Y equals b is a horizontal line. Okay. And so what that's going to mean, and there's a way that you can set this up in terms of an integral in x, but it is no fun. Okay, it's much simpler to set up. And in fact, I don't know if you have the techniques needed to solve that. But either way, we're not going to try to solve this type of problem with an integral in x. We're going to just do it with an integral in y, and it's going to be so much easier. Okay. What we're going to do is we're going to say, okay, wait, this is y equals the square root of x. And so if I was going to integrate right minus left in terms of y, I need to solve for x. So I'm going to square both sides, and I'll get x equals y squared. That will be helpful. This is y is going to run from 0 to 3. So, but we're saying that if I integrate from 0 to b, that's halfway from 0 to 3. Okay, that's one way that we could write an equation. Integral from 0 to b of right minus left is x equals y squared minus x equals 0. That's equal to the integral from b to 3 of y squared dy. That's our first option. And wait, yeah, no, that's one I like better, is that this area is equal to that area. Another option you do have, though, is, and I'm going to do this up here because I don't really want to do that, 0 to b of y squared dy is going to be equal to half of the entire thing. You can even see that. Half of the integral from 0 to 3 of y squared dy. Okay, I don't just love this technique. I kind of like, actually, it really doesn't matter. It's the exact same thing. But I have always kind of set them up as the two are equal, and you can solve that way. You can do the other one. Doesn't matter. You solve it for b. Okay, so we know how to take this integral. We add 1 to the power, and we divide by the new power to get ourselves an antiderivative. We plug in the top and bottom, and we subtract. Okay, so 1/3 of b to the third minus 0 equals 1/3 of 3 to the third. I know how to do that. 3 to the third is 27. Divide by 3, that's going to be 9. Minus, and then when I plug in b, I'm going to get 1/3 b to the third. Yes. Minus 1/3 of b to the third. So, I'm going to add this over here. And I'm going to get 2/3 b to the third equals 9. Multiply both sides by 3, and I get 2b to the third equals 27. Divide by that 2, and we'll get b to the third is 27 divided by 2. And that means to me that b, if I take the cubed root of both sides, I'll get 3 over the cubed root of 2. And that's the value of b. It's a magic value. Which, well, it's definitely less than 3, right? Because the cube root of 2 is bigger than 1, so, it makes sense. Okay. It would be between 0 and 3. as to my hypothesis, I got to think that this is a bigger number than 1.5, right? It's got to definitely favor the top side because there's more area up there. That was number 10. Number 11, find the exact value of the area enclosed by y equals e to the 3x, x equals 0, y equals negative 2, and x equals 2. That's a lot of curves, so let's just try to sketch the region first. So I'm going to need x equals 0 and x equals 2. X equals 0 is the y-axis. X equals 2, well, let's just say it's right here. Y equals e to the 3x would start here at 1, and it would definitely increase really fast. But, you know, this is our drawing to make it, you know, increase so fast. And then y equals negative 2, maybe we'll say that's right here. And we'll go and we'll make ourselves that. All right. So we can see that this is kind of the area that we're wanting. It kind of straddles the x-axis. But we don't care. We don't care if it goes negative down here because we're just going to do top minus bottom and it'll take care of that. So I'm going to go over here, say top minus bottom, draw my representative rectangle. And again, the reason for drawing the representative rectangle will become more obvious, you know, the next couple of classes when I tell you about how to find volumes that you get by rotating things. You need to kind of track a representative element. In this situation, I can just remember top minus bottom, but I'm going to keep tracking the representative element. This is y equals e to the 3x. And this is y equals 2. So top minus bottom, y minus y. That's what I'm going to integrate. And I'm going to integrate as x runs from 0 to 2. And it's going to be y equals e to the 3x minus y equals negative 2. Okay, I mislabeled this, but this is definitely y equals negative 2 there. And I'm letting x run from 0 to 2, so I integrate with respect to x. I'm going to find an antiderivative for e to the 3x. An antiderivative for e to the 3x is going to be 1/3 of e to the 3x to account for the chain rule, plus 2x, and then I need to let x run from 0 up to 2. And then that's going to be equal to 1/3 of e to the 6 plus 4 minus, when I plug in 0, it's not just going to be 0. It's just not automatically, you can ignore anything when the bottom bound is 0. Because when I plug in 1/3 e to the 0, that's 1/3 of 1. And then plus 0. Okay, and that's a good solid exact value. Okay, but yeah, again, you could turn that into a single fraction if you felt like you had to, but I'm telling you, you don't, so I don't see why you would. Set up, but do not evaluate. An expression involving more than one integral. It gives the area enclosed by the graphs of f and g. All right, well, let's just make a sketch of this region. I think it will be more obvious what they're getting at. Yeah, I know why it says more than one integral also. It's like, why would it say more than one integral? So f of x equals 4x to the 2 minus x to the 3. I'm going to actually kind of rewrite this a little bit. So negative, and I'm going to factor it as well. Right, yeah. Okay, so negative x squared times x minus 4. And, you know, on this type of problem, we really don't do this type of problem algebraically anymore. So, like, sketching it yourself, you could probably use a calculator. Realistically, if you were going to encounter this problem on an assessment or something, you'd probably just be given a picture of the graph and asked to choose amongst a list of integrals which properly represents the area that they're talking about. Anyway, that means that f looks a little bit like, pardon me, it's a little rough looking. So it's a negative leading coefficient third degree polynomial. So it's going to come from above, it's going to balance at x equals 0, and then it's going to pass back through at x equals 4. So I'm going to do that. Then, you know, I mean, it might not be perfect, but it will work. So, and g of x equals 3x. All right. I think what's going to happen is I'm going to redraw that sketch. Okay, so I just made a new sketch. It is probably honestly worse than the original, right? But it somehow is going to make it easier for me to draw in the second curve. And I'm looking for my straight edge, not finding it. Y equals 3x. Who knows? I don't know. I know it goes through the origin. I don't really care about the relative steepness. So I'm just trying to draw you a picture anyway. And there we go. That will do it. Okay, so really I want the total of these two areas. Okay, that's why they said more than one integral. Because we could just say it's just you integrate from 0 to that intersection point, the absolute value of f minus g, right? That would always be positive. I wouldn't have to worry about which one's above the other one. That would be way easier. They said more than one integral, and that's kind of what they were getting at, is you can't just kind of cheese your way through it by saying, oh, I'll just take the integral of the absolute value and be happy. Okay, so now my job is to figure out, okay, I know they intersect at 0 because they both contain that point. I need to find the x coordinates here and there. But we can do that by setting the two things equal to each other. So I'm going to kind of go off to the side. Maybe I'll come back to that sketch in a minute. So f equals g, finding the x coordinate. So that's 4x squared minus x to the 3 is equal to 3x. And maybe I'll set this whole thing equal to 0 by subtracting. 0 equals x to the 3 minus 4x to the 2 plus 3x. Let me tell you, this is going to be factorable. 0 equals x times x squared minus 4x plus 3, which can then be factored itself into x minus 3 and x minus 1, meaning that, okay, this is equal to 0 when x equals 0, x equals 1, and x equals 3, which happen to be my three x coordinates of intersection. So that'll be 1, and that will be 3. So now my job is going to be, and maybe I'll actually label these f is the curve and g is the straight line. And after all of that, I've got this to look at right here. So if I want to write one expression that has more than one integral, I'm going to say, okay, the first one, and maybe, you probably won't be able to see this, but I'll do this one in blue. Okay, the blue integral is going to be the integral from 0 to 1 of top minus bottom is line minus curve. So the line was g of x minus f of x. Okay. Then I'll add in red, I'll do this area. Okay. And then that will be the integral from 1 to 3. Top minus bottom will be curve minus line, that's f minus g. And then that's how I'm going to write an expression with more than one integral. Write one integral to represent the area of the shaded region. Well, if I tried to do this in terms of x, right, top minus bottom, I'd have two different things going on. Because for a while I'd have this slanted line minus the flat line, top minus bottom. But then after a while, kind of once I went past x equals 0, I'd have this flat line minus the slanted line. And that's not going to do it. Okay, now maybe we could do that and double it, but what we're really getting at here is that if you integrate in terms of y, it's always the same right and left. So it'll always be this line on the right and that line on the left. We can let this kind of horizontal representative rectangle slide up and down the y-axis, and we'll get ourselves an area. So we're going to let y run from -2 to 2. And then right minus left, well, I guess so our job is to not only do this, but find a curve for these as well. Okay, that's fine. We can do it. I think this is going to be y equals x minus 2. And well, I bet this is going to be, y equals x plus 2. Okay, we can do it. Now, but if we're integrating in terms of y, we need x equals some function of y. So we're going to solve for x. So this is y minus 2. And this is going to be x equals y plus 2. So what I'm going to have, right minus left, on the right I have x equals y plus 2. And on the left, I've got x equals y minus 2. Ah, yes. And that makes sense, because I was kind of looking at this and I was like, man, isn't the width of this rectangle going to always be the same as I slide it up and down? And it definitely is. And so that's why I'm just going to be integrating 4 with respect to y as y runs from -2 to 2. Okay, that's cool. Let's keep moving. Okay. Find the area of the region enclosed by the graphs of f and g. All right, that is a parabola and another parabola. You can't even see that. Okay, let's look over here. Okay. I think I'm going to try to do this one without a calculator to show you, it can be done. I'm going to start kind of like I did the other one. I'm going to make the sketch and try to see if that shows me anything. As best I can. I'm not going to sketch it on the calculator or anything like that. That's the pen I was using. Okay, so x squared minus 4x plus 3. We just worked with something like that. That's going to be x minus 3, x minus 1. And maybe because I don't know what the zeros of this thing are going to be, I mean, it looks like probably 1 and 2 and -1 or something. Anyway, I'm going to just call that 2. Okay, that's the first parabola, that's f. G is the negative of x squared minus 2x minus 3. So I think that would be x minus 3. Whoops, you can't even see that. X minus 3x plus 1. Yeah. Okay. So, and it's negative, so it's going to open down. So it'll be x minus 3, x plus 1. And, maybe, it's... Now, I don't know that this is happening to the right of the y-axis, really, right? I drew this one really not proportional. But I do know that there's going to be 2 intersection points. I'm going to have G over here on the interval that they're sharing, that's, the area that's enclosed by them. G is going to be above F. So I think I got an idea of what I'm doing here. So what I'm going to do is I'm going to actually find that coordinate of intersection. I know that's going to be 3, right, just for my sketch. So I need to set them equal to each other. F equals G. So x squared minus 4x plus 3, I'm just copying, equals negative x squared plus 2x plus 3. Okay, now I'm going to set this thing to 0. I'm going to add x squared, 2x squared, subtract 2x minus 6x equals 0. That's helpful, right? I know that's going to be equal to 0 anytime that 2x is equal to 0 or anytime that x minus 3 is equal to 0. We already knew about that one, x minus 3 equals 0. That means that this is actually happening right there on the y-axis, okay, which I thought might have been the case, but I just didn't want to do the wrong thing. Okay, so I've got x equals 0 and x equals 3. And so I'm going to integrate, just kind of pretend that y-axis isn't there. And I'm kind of realizing, looking back, I shouldn't have even drawn the y-axis, just drawn the parabolas until I got the intersection. Anyway, so I'm going to integrate from 0 up to 3 g minus f. G of x is let's just figure out what g of x minus f of x is in general, and then we can just throw that into the integral. Okay, so g minus f would be negative 2x squared. 2x minus negative 4x is going to be positive 6x. 3 minus 3 is 0. Okay. So, makes sense. I was looking for where g minus f was equal to 0 also, so it's all good. I'm ready to go. So, equals the integral from 0 to 3 of 6x minus 2x squared dx. Now I'm going to find an antiderivative. That will be 3x squared minus 2/3 x to the third as x runs from 0 to 3. And 3x squared will be 27 minus 2/3 of x to the third. X to the third was 27, 2/3 of that's 18. And when I plug in 0, I'm going to get 0 on both of those terms, so I'll just have 27 minus 18. That's going to be 9 units of area. Okay. The shaded region in the first quadrant bounded by cosine of x and y equals 2x. Figure is not drawn to scale. Yeah, because if you look at the old versions, the quiz I used to give on this topic, you'll see that I used this one figure for a few different scenarios. I think I might have said it was y equals x, might have said it was like y equals 3x, you know, all those different things. Slightly change it up, right? So, but what we need to do is that's not good. Somebody must have borrowed my calculator. Okay, and I've told you this before, but anytime you're graphing something and you put an integral into y equals, it's probably not the right thing to do, and it's going to take your calculator a really long time to graph it. Okay, so y equals cosine x, and y equals 2x, and maybe I will, yeah, okay, this is a bad sign here. Okay, so we're going to, what am I going to do here? I'm going to do zoom standard, which you press zoom and then 6. To the standard window. And that might end up zooming in on it, but probably not, right? Because if they're only intersecting once, I need to calculate the intersection between blue and red, which happens to be at x equals 0.4501831. Okay, so I just solved an equation using the calculator, so I need to report what equation it was that I solved. Moreover, since this solution to that equation is not the final answer that I'm looking for, I'm not going to round it to 3 decimals. So 0.18361, which may be really annoying to you, and I get it. It's a lot of decimals to copy for something that's not that important, but round this off at your own risk, right? It could be that cutting off the 18361 does make a difference when we integrate in the last decimal place. And, there's not really any sort of like, oh, there, you rounded early, but you did the process right, so I'm going to give you the credit. It's like either you got the right answer or you didn't. And if you didn't, whether you made a calculus error, an algebra error, an early rounding error, these are all errors, and if you're not right, you're not right. So I'd recommend carrying all the decimals if it's not the final answer. So I'm going to integrate from x equals 0 up to x equals 0.4501831, top minus bottom. Well, in this case, top minus bottom is going to be y equals cosine x minus y equals 2x. And so that's what I'm going to integrate on. Couldn't even see my representative rectangle. So cosine x minus 2x, and we're going to integrate that with respect to x. Okay. Because of that, in fact, I've already used the calculator to find the intersection anyway, I'm going to use the calculator to find the area. Okay, so integrate from 0 to 0.4501831 cosine x minus 2x dx. I get 0.232. Okay, sure, that looks possibly reasonable. It wasn't really drawn to scale, but it's definitely less than 1, right? That's what we need. 0.232. I did round that to 3 decimals because that's the number that I've been tasked with finding in the first place, the area of the region. Okay. That's something that we can round to 3 decimals. Right, but do not solve an equation involving an integral whose solution gives the value of k for which x equals k, splits the region into 2 equal areas. Okay. Well, that's pretty much like, I'll just try to give you a new sketch. That would be like, okay, x equals k is a vertical line. I think it's going to be like maybe around, whoops, that wasn't actually all that vertical. Maybe it's about like that, where it splits it in half. Okay, and that's x equals k. So if I integrated from 0 to k on top minus bottom, that would be equal to integrating from k to the intersection point. Or you could say it was half of 0 to the intersection point. Or maybe, since I just did that work, I will say half of, I'll copy all the decimals. 2 principled. So 232, 4655, 752. Okay, that's another thing, since I just already did that. I could say that's an equation whose solution would give the value of k that made that work. Find the perimeter of the shaded region. Okay, we've already been working with this region, and yes, this will be fine. Skittish about these perimeter integrals after that one earlier, but it's all good. Okay, the perimeter, I'm going to say that's 1 unit of area, or 1 unit of length. This is going to be 4 units of area, or of length, pardon me. This is going to be 3 units of length. And, hold on, I lost myself. Really, I was trying to remember how I got the scale to be different in X than in Y on my usual graphing software. I don't remember how I would have done that in the past. But you don't care about that. That's not what you came to watch. Okay, so we're going to say, all right, I've got 4 and 3 is 7, and 1 is 8. Plus the curved part, that's something I'm going to have to use an integral to find. So if y equals 6 over x, that's like saying y equals 6x to the negative 1 power. I need dy dx in order to find the arc length, so that would be negative 6x to the negative 2. And that's what I'm going to need to square, add to 1, and take the square root of in order to find the arc length. So this will be the integral from x equals 1 to x equals 3 of the square root of 1 plus dy dx squared, so negative 6x to the negative 2 squared with respect to x. Now that one requires a calculator. I don't know, maybe not. I don't see any way in which that doesn't require a calculator. Sometimes these are like, you can use a trig substitution, or some things that we don't actually do in AP Calculus to find these bad integrals, but I don't know about this one. Even if we could, not something you need to worry about. Negative 6x to the negative 2. Oh, you can't even see that. Okay, we're not going to forget to square that. It's the most common issue, besides forgetting to press the integral button, and that's just not going to work. I can't insert an integral. So 8 plus the integral from 1 to 3 of and I got 12.609. Right, if f of 1 is 5 and the length of the graph of f from 1 to 3 is given by that integral dx, lost my dx, write an equation for f of x. Okay, what this is telling me is that this thing right here is related to the derivative, right? If we think about the arc length formula, it's 1 plus dy dx squared. So that means dy dx squared equals 16x to the 6. Or maybe I could call it f prime of x. So f prime of x squared is equal to 16x to the 6, indicating to me that f prime of x could be either 4 or negative 4x to the 3. And I feel like this has a I feel like I need another piece of information here. F of 1 equals 5. Whatever. We'll find out. Okay, so I'm going to anti-differentiate, and I'm going to add 1 to the power divided by the new power. So this is looking good so far. is plus or minus x to the 4 plus c. But it's like, I feel like the first piece of information will help you find c, but then you'll still be stuck with this plus or minus. Okay, so what I'll do, I think I remember this problem. Let me look at the old answer key. It's something I hadn't thought to do. Homework 8-1. I'm just going to go to the previous year. But I think I remember this happening in the past. It's just this number 18. Yeah, okay, I see I've got two answers here. So, in the event that it's the positive, and in the event that it's the plus x, the positive x to the 4 plus c, well, f of 1 would be 5, and so 1 plus c equals 5c is 4. So, on one hand, f of x equals positive x to the 4 plus 4. Yes, because 1 plus 4 is 5. On the other hand, maybe f of x equals negative x to the 4. In that case, when I plug in x equals 1, I'm going to need 1. I'm going to have negative 1 because exponent of 4 before multiplication by negative 1, right? So I've got negative 1 plus c equals 5. That would be plus 6. And it's, how do you want it? Either way. Okay. Presumably, if you saw that problem again where it gave you the arc length integral, oh, I need to think about that. I may have put that on the quiz. You would have at least one other piece of information to show you that it was one or the other, but definitely not both. And, okay, write an integral with respect to represent the length of the graph between x equals a and x equals b. Okay. Let me do dy dx. Derivative of 1 is 0. The derivative of minus cosine is positive sine. Leave the inside the same, right? And multiply by the derivative of the inside. The derivative of the inside is the derivative of x to the 1/2 with respect to x, which is going to be multiplied by 1/2 x to the negative 1/2. Okay. I might actually rewrite this because I know where this is headed. This is sine of square root x divided by 2 square roots of x. So if I wanted to write myself an arc length integral, I'd say, okay, well, the integral from a to b of the square root of 1 plus, well, dy dx squared is going to be, well, if I square the sine, that's going to be sine squared. Okay, and the argument of the sign will not be changed, right? It's sine of square root x. Basically what happens to a number, if you kind of track it, you take a number, you take its square root, then you take the sine of that, and then we're going to square that. That's not going to really impact the x getting square rooted before the trig happens, right? So it's just sine squared. Divide by, okay, this thing, if we squared that, though, that would be 4 and an x. And that is not the type of thing we know how to anti-differentiate, so we just write a dx and we're going to be happy with that. Okay, last page. Let R be the region bounded by log of x squared plus 1 and cosine of x. That's interesting. I don't remember this problem. Give a sketch of region R. Well, I don't know about you, but I don't just know off the top of my head what this thing looks like. I think I have a pretty decent idea, but I'm not sure. Okay, this, I know what that looks like, but still, you know, like, let's go ahead. Have a little look here. So f of x is, whoops, log of x squared plus 1. Second y is going to be cosine x. And, well, let's just zoom standard, see what that looks like. Okay, yeah, I thought that might have a sharp corner. Oh, okay, yeah, we can do that. All right, so we can do a sketch of R. It's not the best ever. Oh, maybe it is smooth through there. Yeah, I mean, the derivative exists at x equals 0 because the derivative of log of x squared plus 1 would be 2x over x squared plus 1, and it would, yeah, it's going to be flat. Just the way it sketched it on the calculator didn't really seem like. I'm not really going to worry too much about the. I feel like I messed up the concavity of f here, but who cares, right? Okay, that's the sketch of R. Find the area of region R. Well, I'm going to need to find the intersection coordinate here, so I'm going to just do that real quick. Okay, remember, if I'm going to solve an equation using a calculator, I need to report what equation I'm solving. That's where f equals g. And we're going to calculate the intersection between blue and red. That will be 915.85766. And okay. Then now, if I want to find the area of region R, I'm going to integrate from 0 to that, and then I'm going to, oh goodness, yeah, and then I'm going to double it. Okay, but since I'm going to need to use that number for this area and the perimeter, I'm going to store this number. And I don't know if I've shown you how to do this in class yet because I haven't had that class yet. I'm kind of pre-recording these answers. So I'll show you now if I haven't yet. So what we want to do is we want to take this point 915857766. We want to store it. Okay, so we hit the stow button right there one time, and it gives us the arrow. And then we choose a letter to enter it in. Let's just say A. Okay. So I'm going to store it, stow it, and I press the enter button. And it just says, okay, I put that in A. Now when you type A, I know you mean 0.915857766. Okay. So what we're going to do is now we're going to integrate from 0 up to A. Now, if, like on the test or in the pre-response section of your AP exam, we're going to want to say, be very explicit about let A equal 0.915857766. Okay. And then we can now say it's twice the integral from 0 to A of, let's see, that would be cosine of x, so g of x minus f of x dx. And that's going to equal, well, we'll find out what that equals. 2 times the integral from 0 up to A, and we just type in, whoops, that didn't go well. Okay, and then we're going to type in g minus f is going to be y2 minus y1. Make sure, yeah, that's it. And with respect to x, and I get that amount of area. So 1168. Perimeter of R. All right, so what we're going to do is we're going to split it up. All right, so f prime is equal to, like I said, all right, it's 1 over x squared plus 1 multiplied by the derivative of x squared plus 1 for the chain rule, right? So that would be 2x. And g prime of x equals negative sine x. Now that I've written down what these are, and I actually, can say what I'm talking about, I'm going to integrate from negative a to a. Or you could do 0 to a and double it. I don't know which would be faster for the calculator. I don't know. And that would be, I'm just going to do maybe the top portion of the curve, which would be on the part of the curve that's like, or the top part of the area, which is the curve y equals cosine x. So 1 plus, this would be negative sine x squared dx plus the integral from negative a to a of the square root of 1 plus f prime of x squared. That would be and it's definitely something we could do with a calculator, and I'll just say I think y'all can type this into the calculator. If you're having a tough time, use the fraction bar, be careful about your parentheses, the whole thing. You do that, eventually you get it's 4.282. Or at least that's what I got last year. All right. Table below gives information about f and its first derivative. Use a right Riemann sum to approximate the, yeah. I think that wanted to say using. This one's got multiple typing errors. It's embarrassing, but it's going to be all right. Approximate the length of the graph of f on the interval 1 to 7. Okay, so I would want to do the integral from 1 to 7 of the square root of 1 plus f prime of x squared. And so I know I've taken this question before. You know, like how do you actually run a Riemann sum on something that's not just an area, right? Something like volume. Well, what we do is we're just going to take that integral and turn it back into a sum. So it would be the sum of rectangles that have width delta x. Well, we know how to find delta x, and have height given by the square root of 1 plus f prime at some particular point. But if we're going to use right Riemann sum and the subintervals, then we're going to have, basically we need f prime at the right edge. So that would be 5, 2, and 4. So it would be the square root of 1 plus dy dx squared multiplied by delta x plus 1 plus dy dx squared delta x, that's another 2, plus 1 plus dy dx squared would be 16. Okay. Width, again 2. And that would be, that's good enough, right? We don't know the square root of 26, 17, and 5. Okay. We could combine those. I know there's a multiple choice question out there that looks a lot like this one. Just gotta mention that. So let f be the function with f of 0 equals 0 and f prime is that. Why do I need f of 0 equals 0? I'm trying to think if there's something I'm not thinking of here. Okay, I mean, there wasn't when I worked it last time. That's kind of the fine print that you usually need to worry about, right? In this class, kind of an analysis level consideration. Anyway, we're just going to go 0 to 5. Integral from 0 to 5 of the square root of 1 plus f prime of x. I'm not copying that. Squared dx. We can do this. Let's get that in here. So the integral from 0 to 5 of the square root of 1 plus, that's gonna, okay, put the fraction bar in there. Log of 1 plus 4 to the x, serious derivative here, divided by x plus 2. Got the squared. Don't forget to square the derivative. 1 plus dy dx squared dx. All right. I would have thought that would have taken the calculator much longer to compute. 6.259. All right. Find the area enclosed by the graphs of that and wait, x squared minus x minus 8. I'm missing something here. Let's do this one with a calculator. Okay, I've been working this problem set for quite a while now, and I think I'm ready to be done with it. So x to the third minus x squared minus 8x and x squared. Okay, and maybe with any luck, yeah, that's not so bad. Oh, interesting. Okay, so we'll find the first intersection. All right, x equals -2. You could barely see that, pardon me. Okay, so the first intersection is happening at x equals -2. So I need to integrate from -2 to 0 on the blue minus the red, which would be, okay, x to the 3 minus x squared minus 8x minus, bottom would be x squared, so I'll make that minus 2x squared, plus, and then if I go over here, and here I've got the intersection again, but I need to probably let the window go a little higher. That was not what I meant to do. I want the y to be more extended. Yeah. So hopefully... There we go. Okay, so we're going to find the intersection there. It's 4 and 16, so x equals 4. And then so it'd be the integral from 0 to 4 of x squared minus that. So, okay, if I took really y2 minus y1, right, I would have negative x to the third plus 2x squared plus 8x. Which should be, yeah, if you do it right, it should be the opposite of the other one. We can run that through the calculator or whatever. And, oh man, I did this by hand last year, and I'm glad I didn't do it this year. It was a lot of algebra. Another idea that I had was, you know, I could integrate from -2 to 4 of the absolute value of y1 minus y2 on the calculator, or the absolute value of y2 minus y1. And that would just kind of blow through everything, and that would give you your answer of 36. Okay, if you need practice on integration, this is the type of thing you need to integrate to make sure you can turn that into 36. If you can't, then you need to come talk to me, and I'll work with you on it, because we can make that happen. Okay, 1 over 1 plus x squared and y equals 1/2 x squared. Okay, that's cool. I'll do this one by hand. This one is one that you probably would need to be able to do by hand, not all the way through, but like there are various things that you need to know about it. So let's first draw a sketch. Okay, what does the graph of 1 over 1 plus x squared look like? It looks like that. What does 1/2 x squared look like? Well, we know that's a parabola, and it's a little wider than the average parabola, but it'll be about like that, right? So let's find the x coordinates of their intersection. This thing, based on the squares, I know it's got to have that symmetry across the y-axis, so I'm probably just going to find the ones, but we'll probably see it in the algebra also that it's going to be, you know, whatever this is, that will be the negative of it. So 1 over 1 plus x squared equals 1/2 x squared. Okay, multiply both sides by 2. Maybe cross multiply. Okay. Set to 0. And oh, yeah, okay, we can factor this. We just have to be smart, right? This is like if you saw 0 equaled t squared plus t minus 2, we would say that we could factor that, right? We could say that's t plus, well, that's not going well. Let's say that's t plus 2 multiplied by t minus 1. And, yes, t in this case is equal to x squared. So it's going to be 0 equals x squared plus 2 multiplied by x squared minus 1. X squared plus 2, that doesn't pull back any real numbers if we set it equals 0. This will give you x equals 1 and -1. So all that work to say that's 1 and this is -1. Okay, that's cool. We're not scared of a little bit of work. So what we're going to do now is we're going to integrate from -1 to 1, or I think I'll probably integrate from 0 to 1 and double it. So actually, looking at how the work ends up going, I'm gonna go -1 to 1 just to remind you about something about trig. What does this have to do with trig? Should just have to keep looking. So top minus bottom, that's 1 over 1 plus x squared minus 1/2 x squared. Okay. Antiderivative for 1 over 1 plus x squared with respect to x. You got to know it. It's arctangent. Okay, add 1 to the power, divide by the new power. Let x run from -1 to 1. Okay. Okay, and then I plug in -1, and that 1, so it would be plus 1/6. All right, now, back in time a little bit to the unit circle. Okay, arctangent of 1 and arctangent of negative 1. Okay, arctangent takes all its values in these two quadrants. It's just like arcsine. And arctangent of 1, you think to yourself, where is the most obvious place on the unit circle where tangent equals 1? Think about it for a second. Hopefully you're just thinking, okay, oh, I know what it is. If you don't, what we're going to do is, okay, tangent is positive. Well, that's probably happening here in the first quadrant. And if tangent is going to be equal to 1, well, I mean, I need like 1 and 1 or 2 and 2 or something like that. And I need to have the same x and y coordinate on the unit circle. And that's another hint. Regardless, you need to just know that inverse tangent of 1 is pi over 4 in this class. Okay, you got to have it. Okay, you don't need a whole lot. I don't think you really need any other inverse tangent points besides, inverse tangent of 1, inverse tangent of negative 1, inverse tangent of 0. Can't really think of any others. Theoretically, maybe inverse tangent of square root of 3 or 1 over the square root of 3 or something like that. But probably not. Just 1 and 0 most likely. So that's pi over 4 minus a sixth. Minus, okay, arctangent of negative 1 is the most obvious place on the unit circle where tangent is negative 1. Well, that would be this, right? Where tangent's negative 1. And that would be where theta is negative pi over 4. And then there you'd go get, I think, pi over 2 minus a third. That's what I got last time. Yeah. Okay, and that's going to be all I got for you for this video. Okay. If this was not enough for you, you still need more practice on integrating areas with respect to y, something like that. I've got more videos, more examples, and I'll have those split out by topic. So if you wanted, more examples of area, then you could go find that. If you wanted more examples of arc length, then I'm going to have that in a separate video. But, this video is certainly long enough. Thank you for watching. I hope it was helpful. And like I said, if you need more support, you can either come talk to me or you can watch the other videos of more examples. Take care.